Hi everyone, our final year project is custom algorithms to image transgenic jellyfish. This figure shows a transgenic jellyfish. It is a transparent creature that is genetically engineered to help neuroscience research. And since they are transparent, we can observe how neural activities are happening inside them. This helps to understand how their neural activity relates to their behavior. The imaging of this jellyfish is currently performed in 2D using fluorescence microscopes. Two dedicated channels are utilized for capturing two distinct fluorescence light emitted from this creature. As shown in this video, the channel 1 captures the neurons only when they fire up. The channel 2 displays all the neurons within the jellyfish. Next, I will discuss how these images are formed in the microscope. The point spread function is an important component in the image formation in microscopes. It describes how an imaging system captures light from a tiny point source without focusing it to a perfect point, but instead creating a blurred pattern. Therefore, light coming from points that are not in the focal plane will also be recorded in the image as blurred points. So the PSF allows the depth information from other planes also to be included in the image taken from the focal plane.
In this project, our goal is to track neuron activity and correlate it with specific behaviors. To achieve this, we first need to accurately monitor the intensity of neuron signals over time. One approach is to focus on a fixed area, such as the red square shown here, and calculate the mean intensity of the target neuron within that region across all the time frames. However, because neurons can move significantly, this fixed area approach fails to provide accurate measurements. To overcome this, we use a two-channel tracking method. Channel 2 allows us to track the neuron's location, while Channel 1 measures the intensity. By dynamically tracking the neuron's position, we can get a more precise measurement of its activity. In this figure, the blue plot shows the intensity variation over time without tracking. In that, we can see the neuron moves out of the red square, especially around frame 120. The yellow plot shows the intensity with tracking, where the neuron stays within the tracked area. As a result, tracking the neurons is essential for detecting changes in activity. Without tracking, we would miss critical variations such as those seen in figures for 0.4 and 0.17. However, there is an additional challenge. Neurons can sometimes go out of focus and then reappear due to depth changes, making it difficult for tracking algorithm to identify the same neuron when it returns. To address this issue, we are working on reconstructing the jellyfish in 3D. This will not only help us track neuron activity more accurately, but also enhance our understanding of the jellyfish behaviors in three-dimensional space. As we mentioned earlier, we must track the neurons to observe their activation patterns. To track the neurons, we use CoTracker, one of the best methods for 2D tracking. For 3D reconstruction, we use a customized version of OmniMotion method and use the optical flow data which we obtained from CoTracker to further enhance our 3D reconstruction.
In our scenario, we only have monocular single-view video captured from a microscope. But because of the transparent nature of the jellyfish and by utilizing the depth information by incorporating our point spread function, we will be able to achieve a better 3D reconstruction of our jellyfish. For the 3D reconstruction, we have chosen OmniMotion-based architecture with a canonical space representation. In this canonical space, it has all the pixel information. So, if one pixel information missed, it can be retrieved by this canonical space. We did some improvements to this OmniMotion architecture. First, we introduced a new loss function by incorporating our point spread function. Another improvement we did was we replaced the noisy correspondence which we used to calculate the flow loss with CoTracker method. To reduce the training time, we only use selected pixels after applying a foreground mask. Thereby, we were able to reduce the training time by 25 to 30%.
Initially, we explored generating 3D point clouds using nerve-based approach, but it didn't yield accurate depth information. This was because it used only single view data and didn't consider the temporal movement of the jellyfish. Our OmniMotion-based 3D reconstruction, however, does incorporate temporal information, and with the introduction of the PSF, we have achieved much more accurate 3D point clouds. Here you can see a comparison of the original video, depth map, and the depth overlaid video, all generated using the OmniMotion-based method. When compared to the best existing approaches like Depth Anything and Marigold, our method performs better, especially for jellyfish data.
With that, we have come to the end of our video. Thank you for watching.